All right. So I thought of discussing last year CAT paper and also the final exam question, a related question to Unit 3. And then if time permits, we will go back to our presentation. I prefer to do some Miller indices questions and then about the defects. So defects part is very easy. Everything is well written in the session, okay? Crystal defects. But thermodynamic part, I want with just one slide, I want to discuss that with you in case you don't understand it better. Right. Okay. So we will start from here. Let me check whether I can write on this. Yeah. You all see the doodling, right?
Yes, sir. Yes, ma'am.
Okay, good. Okay. Now, this is the last year CAT. Last year, it was somewhat different. We had both MCQs and structured. But this time, as I mentioned last day school, during that last day school, we will only have MCQs. 20 MCQs, 10 from Unit 3, 10 from Unit 1. Okay? All right. So, here, the first one. Now, you guys have to answer these questions. We will discuss it together. So, covalent crystals have higher melting points than molecular crystals, then lower. If we discuss about that, so in molecular crystals, there are individual molecules and they are attracted to each other. They are also packed and they are attracted to each other through weak van der Waals forces. Right? When it comes to covalent crystals, what is the difference? What do you expect in the covalent crystals? Now you guys need to discuss, talk. Someone is sending a message saying 10:30 we will have biomolecules lecture. Well, we are supposed to finish at 10. So we will try our best to finish by 10 o'clock. If not, 10:15. Before 10:30, I will stop. Okay? Right. So what do you know about covalent crystals compared to molecular crystals? Molecular solids? Now, if you want to expedite this session, you need to answer. So, what is the difference? What do you expect in covalent crystals? Sorry? Hello? So,
The atoms are shared.
what is it?
Then, madam, high melting points, and that
No.
they are.
Yeah, now my question is, now in molecular crystals, single molecules are packed together and they are they are connected through weak van der Waals forces. I'm asking, what is the difference between those molecular crystals and covalent crystals? So these contain those giant networks where all the atoms are connected, interconnected through covalent bonds throughout the materials, like as an example, diamond. Okay. So when it comes to graphene, well, that is also an example for covalent network solid. So in addition to that, so molecular crystal, let's say sugar. So those are molecular crystals. So molecules are packed together and they are in between, they have weak van der Waals forces. So because those covalent network crystals, it's in a network, they are interconnected through stronger covalent bonds, their melting points are usually higher. So this is actually the correct answer. But if we go to the third one, discrete molecules linked by van der Waals forces. So that applies to molecular crystals, not to covalent networks. Then hydrogen bonding. Well, in covalent crystals, it's a giant network. Hydrogen bonding is also possible in molecular crystals. Always excellent electrical conductivity. Not always. Now, graphite is an example where the electrical conductivity is exhibited because it has one free electron from each carbon atom. But not all the covalent crystals are electrically conducting, right? Okay. Then the next question is about X-rays. X-rays are used for studying crystal structures of solids because, now we don't have to go through one by one. Give me the answer. Why X-rays are used? Why not other electromagnetic radiations? Why particularly X-ray? Why X-rays are used for crystallographic data studies? Someone is saying answer is 3. Yes, answer is correct. It's 3, but can someone explain why it is important that the X-rays wavelength is comparable to interatomic distances? What happens when those distances are comparable with wavelengths, with the wavelength of X-ray? What happens? Can someone explain? Real quick. So the reason is when the radiation or these electromagnetic rays, they diffract only when they go through obstacles which are in the comparable or similar in size of their wavelengths. Otherwise, they will not diffract. So we want our wavelengths, our rays or electromagnetic radiation to diffract from these atomic planes of crystals. So because of that, X-rays are more suitable because its wavelength is comparable to interatomic distances. Right. Then the next one is about defects. So which point defect in crystals does not alter the density of the relevant solid? So what is the answer?
2.
Answer is 2. Can you explain it? Why? Why do you say Frenkel defect? What is the reason? Yes? What is the reason? So there should be a reason for you to say that answer is 2. Anyone? Please? What is the answer? If you hurry up, we will have time to discuss more. Please. Why Frenkel defect doesn't affect density?
Because
Ani?
the ion will be in the interstitial position.
Yeah, so someone is asking whether it's okay to explain in Sinhala. Yeah, it's fine. So yes, in the Frenkel defect, the losing atom is going to be nearby. They are in the interstitial positions. So, right. Now, what happens is in other cases, the atoms or the ions that are going to be losing, like as an example in Schottky defect, or if centers, non-stoichiometric defect, there that particular components are going to go out of the, or come to the surface or come out of the solid. Because of the, like they are going to be absent. So because of that, the density is altered. Okay. So because density is mass divided by volume. So you understand why it is going to affect, others are going to affect. When it comes to impurity, then the foreign object or foreign constituents are now in the system. Again, the mass is going to be different. Okay. But in the case of Frenkel defect, it is leaving its original position, but it is going to linger nearby. It is going to be present in the interstitial position. Someone is asking whether it's okay to explain in Sinhala. Perfectly okay. Go ahead, please. I want you to discuss. I apologize that I can't accommodate Tamil because I don't know Tamil, but like English and Sinhala, welcome. Right. Miller indices of this plane. What is the answer here?
1.
1. 220. Now, this is something, there are answers coming in the box also. Yes, 1. So, if I quickly explain how we figure it out, first we have to decide on the origin. Now, in these cases, it's easier because I have already given you, like indicated you where the origin is. So, this is the origin. Okay. So, from the origin, we are going to go along the, wait, something is happening here. Yeah. We are going to go along the directions and see where the plane is going to intersect the particular unit cell length. Okay. So in that case, if you go through the x-axis, you will see that it is going to, it intersected the unit cell length at the midway, okay, half. So first you are going to record all the intersections. Okay, something happened to my writing pad. Anyway, so X, Y, Z. Then this is being intersected at A divided by 2, halfway. Then if you go along the y-axis again, this doesn't say this is a cubic unit cell. So to be safe, we will use 3 different unit cell length. But anyway, along the y-axis, it's been again divided at halfway length. What about z-axis? Where is the intersection? There is no intersection, right? There is no intersection. Okay, all right. So, no intersection, it is going to intersect at the infinity. Hello? Someone is talking? Hello? Any problem? Yes. So then we are going to fractional intersections. We are going to get fractional intersections. What you do here is you are going to divide all these intersections with by the unit cell length. So you are going to divide A divided by 2 by A. Here B, half B by B, and then this by some other value. Okay. Then you are going to get half. So what happens if you divide infinity by some number?
Zero.
No, infinity divided by any finite number is still infinity, okay? All right. Then we are going to take reciprocals. So reciprocals is, you know what it is. So you are going to do this and then this. Okay. 1 divided by infinity is 0. All right. So this is the final answer. This is how you take it. All right. Intercepts, then fractional intercepts, and then reciprocal of those values. And then you write it without any commas and with a curly bracket. Okay. All right. Then number 13, what is any questions there? I hope not. Oh, so then let's go to number 13. What is the answer for that? The formula of a compound in which the element Y forms cubic close packing, lattice and atoms of X occupy 1/3 of tetrahedral voids. So how do you answer that? Yeah, so people are sending me the correct answers. It's 3, but I want to know how you get that. Can someone quickly answer me? Because like by discussing the way you get the answer is going to help you when you are doing similar kind of question. Please, can someone explain in Sinhala is also okay. Can someone explain? Yes?
Excuse me, madam.
Yes.
මේකේ මේ අපි y කියන එක n කියලා ගත්තොත් එහෙම මේ අපි දන්නවා ටෙට්‍රාහෙඩ්‍රල් වොයිස් මේ 2යි n ගානක් තියෙනවා. එතකොට මේකේ x කියන්නේ 3න් 1යි. එතකොට x කියන්නේ n වලින් 3න් 1යි. y කියන්නේ n. ඒ දෙක සුළු කරලා ගත්තාම
n වලින්
x2
3න්
y3
1යි.
කියලා.
Oh, n
2යි n වලින් 3න් 1යි.
අන්න හරි.
Sorry
ඔව්.
madam. 2යි n වලින් 3න් 1යි x. y කියන්නේ n. ඒ දෙන්න සුළු කරලා ගත්තාම x2 y3 කියලා එනවා සූත්‍රය.
හරියට හරි. Exactly. So if I explain it real quickly again, what she said was, now we have to always, there's a one rule that we need to follow when comes to close packing, either hexagonal or cubic close packing. In close packing, if you pack n number of atoms, okay, n number of atoms, either in cubic close packing or hexagonal close packing, it is going to create n number of octahedral voids and 2n number of tetrahedral voids. Now, in this case, they say y is close packed and x is occupied 1/3 of tetrahedral voids. So, if you consider that there are n number of y atoms close packed, which will create 2n number of tetrahedral voids, then 1/3 of those tetrahedral voids are occupied by x. Now you just simply have to simplify this ratio. Okay, n to 2n. Okay, something. I'm so sorry that my notepad is making it crazy. Okay, so 2n divided by 3. Then I'm going to multiply the both side with 3, right? And then divide by n, just to make it a simple ratio, okay? So it becomes 3 to 2. So there are, what happened here? There are 3 x atoms, and for each 3 x atoms, there will be 2 y atoms. So your answer will be, did I do it right? What happened? Sorry. Here, yeah. So because y is the one that close packed, so it has to be changed in that way. This is y, this is x. So for every 3 y atoms, there are 2 x atoms. Okay, good. Like, let's move on to the 14th one. This is actually 2 things coming together, 2 equations. But did you all do this question? Do you know the answer for the 14th question? So you will need to use, answer is 2. Someone is saying, correct. You guys already done your homework. Nice. I know these answers are probably ECT and OULMS, the answers. Anyway, no issue. Either way, I'm glad that you have come prepared. So can someone explain this to me? This one, how do you figure this out? So this is a simple question, but you need the knowledge of the Bragg's law and also the interplanar distancing equation. Okay. Since it is difficult for me to write in here, I'm going to quickly share my slide and then write on the slide. I hope it's okay. Now, can you all see the slide? The presentation slide? Huh? Okay,
Yes,
so
ma'am.
we have,
Yes,
we
madam.
have our Bragg's equation. Okay, and then we have our interplanar distancing equation. You should know this, especially the Bragg's equation, you should know by heart. Okay, but if you are need to use the interplanar distancing equation for a cubic unit cell, I will provide it for you. You don't have to by heart, but if you do 1 or 2 questions with these, it will automatically register in your head, right? Anyway, if you go back to your question real quick, okay? If we go back to our question real quick, it says the metallic silver crystallizes. The metallic silver crystallizes. You can still see the slideshow, right? So metallic silver crystallizes in FCC lattice structure with a unit cell length of 40 nanometers. So here it doesn't clearly say this is a cubic lattice or cubic unit cell, but by giving only the unit cell length, it implies that it is, of course, cubic unit cell. Okay, right. Then we have the A value. You all can see my writing, right?
Yes, ma'am.
Okay. And then it says it's a first order diffraction. So N is given and X-ray beam from 210. The plane is given and then the diffraction angle is given. This is theta. They are asking for the wavelength. They are asking for lambda. So if you try to use just the Bragg's equation, N is given, theta is given. They are asking for lambda, but D is not given. So that's why we need to use the second equation. So in the second equation, D is, we need to find out the Miller indices of this plane is given. Okay, and then unit cell length is also given. So it makes sense to merge these two together and get the question done, the workout calculation done. So usually what I do is I first I'm going to rearrange this second equation. Okay, and then plug that in the first equation. All right, this is just a rearrangement. Okay, then got the reciprocal and got the square root. And then I'm going to rearrange the first equation by plugging the D with what I just obtained. Okay, and here we have N. I'm going to delete that from here and put it over here. So by plugging all the values here, you get lambda. And what was the answer? You already gave me the answer as, let's go back and see. You gave me the answer as 18 nanometer. Any questions there? I hope not. So let's go to the next one. Consider the following statements regarding lattices and unit cell. Lattice points all have identical surroundings. Do you agree? Do you agree?
Ma'am, can you show the previous slide?
What slide? The workout one,
Yeah,
where I did the calculations. Sorry.
yeah, ma'am.
Uh-oh. So the writings, my writings were gone now. Wait.
Okay, ma'am. Thank
Okay,
you.
hi. Can you see now? Can you see
Yeah,
it?
ma'am.
Okay.
Yeah, ma'am.
All right. So I'm just telling you to plug in these values. 2 into sine 30, 40 nanometer. When you are doing these questions, be careful with the units. Then N is 1. And then square root of 2 square plus 1 square plus 0 square. Okay. All right. Shall we go back?
Okay, ma'am.
All right. All right. So if let's go to the next question real quick. Lattice points all have identical surroundings. What do you think? Correct or not?
Yes, ma'am.
Correct. And then what about second one? A given crystal system will have different unit cells depending on the lattice points in the system. Yes, that is also actually true. I hope you remember what we were discussing during our lecture. So we can, someone is saying it's wrong. So, well, it's actually correct because I hope you remember when we were discussing for sodium chloride, you can define several different unit cell styles. Okay, unit cells you can define in different ways. But if you consider those features, right? So you can draw different unit cells, okay? Depending on the lattice points, okay? But like if you consider the features, those important characteristic features, only 1 or 2 unit cells will be applicable. But still again, it can have more than 1 unit cell type for a particular crystal system. Okay, but like by definition, we go for a simplified version. All right, it's actually correct. The unit cell, the third one, unit cell is the smallest building block from which the whole lattice can be built. Is it correct?
Correct.
Yes. So all 3 are correct actually. Okay. Then let's go to part B. This is, as I told you that structured questions were also there. So this is that structured question. This is very easy. It looks like difficult, but it's easy. This is about a lead, metallic lead solid. Okay, its density is given. Its packing nature is given. It's a face-centered cubic lattice. Face-centered cubic lattice. Then actually, the picture is also given to show you how a unit cell looks like for a face-centered cubic lattice. And the Avogadro number is given. The atomic mass of lead is given. They are asking us several questions. Number 1, number of atoms in a unit cell. How many lead atoms are there in the unit cell? 4. This is very straightforward. As long as you know how many unit cells are there for a face-centered cubic unit cell, you know that answer is 4. Anyone wants me to explain further, please let me know. Okay? You have to let me know. Then volume of the unit cell. How do you determine that? Volume of the unit cell. How can we determine that? So you are going to use the equation. All right? The equation I'm going to get a all right. So what is our equation? So our equation is density equals to molecular weight or atomic weight of our compound divided by the Avogadro number, which will give us the mass of one atom or a unit, and then multiplied by how many such formula units or atoms are there in the unit cell, and then divided by the unit cell volume. So they ask us to determine the unit cell volume, this one. Do we know all the other parameters? So density is given, molecular weight, or the, like in this case, it's not a molecule, it's lead atom. So atomic weight is given. Avogadro number is a constant. We know that, and we already determined how many atoms are there in the unit cell. So volume of the unit cell can be determined. Okay. So volume would be molecular weight divided by N, Z divided by D, the density. Okay. So atomic weight is 207. Avogadro number, atomic number of atoms in the unit cell 4, and the density given as 11.25, the 35 maybe, in grams per cubic centimeter. Here, yeah, molecular weight, grams per mole. This is per mole. Okay. Then you will get some sort of answer. I'm going to directly write it down here. 12.11 into 10 to the power minus 23 cubic centimeter. Okay. Then the next question is, they are asking us about the unit cell length. This is the volume. What is the unit cell length? So actually volume, this is because since this is a cubic unit cell, if the unit cell length is A, this is equal to A cube. So in order to get A, you are going to get the root, cube root. Okay. Here it will be coming to 4.95 into 10 to the power minus 8 cubic centimeters. Did you all get this answer? Did you all get this answer? Did you try the cat question? Anyone got this answer? No?
I did the method, ma'am, but didn't get the answer.
But you know how to do it.
Yeah.
Okay, good, good. Right. So, and then once you get the A, they are asking for the, I think, the radius of the atomic radius of lead. So that is easy. I already taught you at school, like, you know, during the day school too. So the diagonal is actually 4R, okay? 4 radii of the lead atom means they are aligned in the diagonal. And if you consider this right angle triangle, okay, this is our unit length A. This is also unit length A. And 4R is the diagonal, okay? Then if we can write the Pythagoras equation for this, then it will be 4R square equals to A square plus A square. So we can simplify this and isolate R in one side and get 2A square divided by 16. This should be square, okay? R square. Then R will be A divided by, sorry. Can't you see?
Correct. Okay, ma'am.
Okay. So A divided by square root 8. Now, once you know A, you can apply that here and get the R value. I'm going to write the R value here. Later on, you can see whether your answers are correct. And make sure here they ask the atomic radius in picometers. Up to here, you get the answers in centimeters. So you need to do a simple unit conversion as well. This one, and then here the answer will be 175 picometers. You do it at home and see whether you are going to get this. All right. Is it clear?
Yes, ma'am.
Okay, then we will move on to the final exam question I gave you last year, gave the previous batch. So this is a diagram below showing the cubic unit cell of an alloy, a metal made by combining two or more metallic elements. That's an alloy containing gold and copper. Now here the first question is define the term unit cell. So how do you define the unit cell? See, it's already in here. The unit cell is the smallest building block from which the whole lattice can be built. Okay, that sort of answer, if you write that, full marks are given. Then what is the Bravais lattice type of this structure? Now by looking at the unit cell, tell me what is the lattice type, Bravais lattice type?
FCC.
Face-centered.
Face-centered. If you say face-centered, 0 marks. Any other answers? Any other answers? So we discussed something similar during our day school too. Remember, I told you cesium chloride cannot be considered as body-centered.
Primitive cubic unit cell.
Yes, this is primitive cubic. Okay? Primitive cubic. Okay, why? Because now you see the corners are lattice points. So corner is equivalent to, like, they are coinciding with gold atoms, Au atoms. So these atoms on the centers are copper. They are not identical. So they are not lattice points. So this is actually a primitive cubic lattice. All right. Is it clear? If not clear, let me know. Then what is the coordination number of Au? Hint is given, count the number of neighboring copper atoms around Au. Now, let's say this one, this is Au, gold. We have to count how many neighboring copper atoms are there. So this part takes a little bit of your imagination. You have to visualize these neighboring unit cells and see how many copper atoms are surrounding this particular gold atom. You have to visualize in your head. All right. So there is another unit cell here, similar to this. Okay. There is another one at the bottom, another one here, another one here, and another one here. There are since this is in a corner, there are 8 such unit cells surrounding it. Okay. Then you have to imagine how many copper atoms are coming from each of those unit cells and neighboring the gold atom. See, now look at this one. So this is a neighbor because they are on the same plane and that is the closest. Similarly, you can expect along that plane, there will be 4 unit cells. 2 coming out, 2 on the plane. So there is one here, and then there are 2 coming, like, coming out of the plane, out of the, what do you call, your computer screen. Do you understand? So on the plane, there are 4. Can you imagine that? Can you visualize that? So on the plane,
Yes, ma'am.
there are 4 copper atoms. Then think about this one. This is on the face, this and this one, these 2. So this is also on the face, right? They are also close, somewhat below, but they are also closer to and can be considered as neighbors, neighboring copper atoms to Au. Now imagine there are 4 unit cell boxes like this, all right? This copper atom is shared by the neighboring unit cell. So it is like for both unit cells, this one copper atom is counted. Here also this one is shared by the other unit cell that coming out of the computer screen. So that is also just 1. Similarly, if you think about the other corner that is like adjoining to this, okay, there will be 2 more copper atoms like this. I hope you understand. Like, this is the best I can explain it. You just need to visualize it in your head. So there are 4 at the bottom that which are closer, like this. And then if you think about the top of the plane, there are similar 4 copper atoms from the top 4 unit cells. So top you have 4, bottom you have 4, so altogether 12. So the coordination number of AU or gold will be 12 here, meaning there are 12 copper atoms around it. So to make it convenient for you to see, I got a 3D structure, but this you have to do in your head. But to make it visualize, I'm showing you this particular what do you call this 3D model. Can you all see the screen? The 3D model, can you see it?
Yes, ma'am.
Not this one. I actually want to share that other one, which is which I can rotate around. Okay, can you see this one? See? Right, see here this unit cell is drawn. If you can't see, let me know. And though you can't see, like you can look at the unit cell and see these are the corner. What do we have here? Corner AU atoms, gold atoms, okay? And then on each face there is a copper atom. If you just carefully see this is the unit cell. On each and every face there is a copper atom. Oh, wait. This one. Then this one is on the face. This one is on the face. Okay. Just did I correctly got everything? Yes, it seems. Okay. Now the question is how many copper atoms are there around one AU? So I'm going to consider this copper atom. AU atom, gold atom. So on the plane, see on the plane, we have 4 neighboring. 1, 2, 3, 4. Okay. Now, if you just imagine underneath, there are 4 more. They are coming from those bottom unit cells. We can't see those unit cells, but there are 4 more closest to. Okay. See, there are 4 closest to. Likewise, on the top also, you can't see the top 4 unit cells. Similar to these ones, there are 4 similar copper atoms on the top layer. So altogether 12. All right. Is it clear? I hope it's clear. So use a little bit of imagination to understand how many neighboring atoms or copper atoms are there around AU. And if you think about the copper atoms, if someone asks how many neighboring atoms, AU atoms are there for the copper, you will see for copper, coordination number is actually 4. Why? If you consider there are only 4 and on top and on the bottom. So let's say this copper, there are 4 neighboring AU atoms, okay, gold atoms, but on the top and the bottom, they are far away. So they can be considered as neighbors. So for the copper in this alloy, the coordination number is 4. This is something that you can think about later. Right. Is it clear? Oh, wait. Perhaps you can't see. Okay, here, I wrote it here. For copper, coordination number is 4. Just think about it at home. See, if you consider this copper atom, it is going to neighboring with 4 gold atoms. And on the top or the bottom, the other closest gold atoms are far away. We can't consider them as neighbors because they are not touching the copper atom. Okay? Is it clear? Just use a little bit of visualization in your head and then it will come to you. The last one, what is the chemical formula? Yes.
Excuse me, ma'am, can you explain the second part of this question?
Okay, since it is 10:18, let me go to the fourth question and then come back to you, okay? I'll explain
Okay.
it again. What is the chemical formula of this alloy? How do you determine that? So I'm going to delete this writings, or at least delete this drawing over here so that you guys can clearly see my unit cell. Okay, so let me know the answer for the last question. What is the chemical formula of this alloy? How do you determine that? So the general chemical formula is equivalent to the chemical or the constituent ratio present within the unit cell. So you just consider one unit cell and calculate all the how many atoms are there from each constituent. Okay. So what is the chemical formula of this alloy? How many copper atoms are there? How many gold atoms are there in this unit cell? Now tell me how many gold atoms are there in this unit cell? How many?
1.
Just one. How come?
One.
Because they are at the corners and each corner atom is shared by 8 unit cells. So 8 into 1, 8. There is only one. Then what about copper?
3.
Very good. So on each face there is a copper atom and then that is shared by 2 unit cells. So there are 6 such copper atoms. So 6 into 1 half, 3. Oh, sorry, 3. Okay, right. So this is the answer for the third one. Now your question, you wanted to learn the second part, where the coordination number for copper is 4. So easy, let's say take this copper. Now for this copper, there are 4 closest gold atoms. If you consider the top or the bottom, the next coming up gold atoms are far away from it. So we can't consider them as neighbors. They are not even touching the copper atom. So we cannot take those as the neighboring atoms. So the number of neighboring gold atoms around a copper is actually 4. Therefore, the coordination number with respect to copper is 4. Is it clear? I can show you in that 3D model as well. Let's say, not that. I have closed it, it seems. Oh, no, it's there. Sorry. Can you see the 3D model right now?
Yes,
Can
ma'am.
you? Okay,
Yeah.
good. All right. So let's say, let's just worry about this copper. No, wait. Let's worry about, let me see. Okay, let's worry about this copper atom. So it is surrounded by, if you carefully see, it is surrounded by 1, 2, 3, 4. Okay, 4 atoms. But in the same unit cell, these are the next, like this is the copper atom we are considering. Okay, this one. So if you consider the next neighboring gold atoms, they are too far away. See, this one is far away, far away, far away, far away. So they are not even close. So they are not touching these Au copper atoms. So we can't consider them as neighbors. So only on the other side, from the other side also, see they are far away from that particular copper atom. So we can't consider them as well as their neighbors. So because of that, you can see when it comes to copper, the coordination number is 4, meaning there are only 4 gold atoms in the neighborhood, in the neighboring position. Okay, that's what I wanted to explain there. Is it clear now? Is it clear?
Yes.
Whoever asked the question? Okay. So those are the only questions that I was planning to discuss. All right. In addition to that, if we go back to the presentation, okay, where we left last time. So, Miller indices, are you okay? Do you have any questions? Miller indices, do you have any questions? Did you guys do these questions at home? I mean, I already sent you the answers. Any questions? So I'm going to go one by one because I'm going through because I couldn't take time to discuss these during DS Day School too. Because I got like not enough time. So if you have any questions in these slides, let me know. Then we can discuss. So this is where that the origin, if the origin is incorrectly defined, you cannot calculate the Miller value. So the origin has to be closer to the plane, and the plane should not go through that origin, whatever the point that you're choosing as the origin, the corner. Okay?
Madam,
Yes.
Miller indices වල මේ step 2 එක පොඩ්ඩක් කියලා දෙන්නකෝ. origin එක ගත්තන් පස්සේ ඊළඟට කරන එක.
මේකද? This one?
ඕකේ හරි කමක් නැහැ. මොකක් හරි example එක.
Yes, I can do that. We will go here. The original, this one. Okay? So, you define the origin and you decide on the directions. Let's say this is Y, this is X, this is Z. Then what you are going to do is we are going to determine the intersections along each axis. Okay? Sorry, this is they have defined as X, okay? Because see, we usually use A along the X-axis. So I'm not going to change that. All right. So along the X-axis, when you go...
Excuse me, can we label the axis on our, I mean, is there a way, can we get as a Y as X?
Yeah. Like, yes. Origin and the directions you can define as you please. Okay. But at the end of the day, if you do it properly, the same plane will get, depending on the origin and the axis direction you are going to defining, the Miller indices will be obtained. No issue. So as long as you define it, no issue. Now that's why in the questions also, in the papers also, I already give you usually the directions or the center. But this one particular logic you have to follow is that you are going to define your origin. You cannot just take any. You have to decide on the origin which is closest to the plane, all right? But that plane shouldn't go through the origin. So closest, this is closest, but it is not going through that particular closest or center, corner. Okay? Do you understand what I'm saying? So for this particular plane, you are not going to pick this as origin because it's not the closest. Okay? Do you understand what I'm saying? If you pick that, you will realize that your plane is not, you cannot define the direction, so you have to shift your origin. Okay? All right. I hope that is clear. So anyway, now I'm going to take the positive direction of Y here, because otherwise if I take this as the Y direction, then you have to go back and the Miller value will be negative. Still okay, but as long as you are showing that your positive Y direction is this. But usually we avoid that and try to take the directions where the Miller values are positive. Okay? All right. If we have the chance to define our axis. If we don't have the chance to define our axis and the axes are already defined for us, then no chance, you have to go along with that. Okay? All right. Hope that is clear. Now, the second step would be to determine the intersections. Okay? Intersections means where that plane is cutting the unit cell edge. Along the x-axis, this plane is cutting at a divided by 2. So your intersections for x would be a divided by 2. For y, it would be the whole b. So the whole unit cell length. And then along the c-axis, it will be c divided by 3. Is it clear? This is actually the second step. Then you are going to get fractional intersection. There you are going to divide each intersection by that corresponding unit cell length. Okay. Then you are going to solve and get a value. Then you have to definitely get the reciprocal. Though it is a whole number or a fraction, you need to get the reciprocal. Okay. All right. Is it clear now? Now it is same for the negative values, negative Miller values also. See, in this case, the previous origin is not suitable. It is not closer. So they have shifted. And because the XYZ directions are already defined, you have to follow the same. So new Y direction is here, X direction here, Z direction here. But in that case, you see along the X-axis, this is the origin, this is the positive X direction. But to meet the plane, you have to go back in the negative direction. So that's why your Miller values come as minus. All right, is it clear? 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 Huh?
Yes,
Clear?
madam.
Yeah.
Clear, madam.
Okay, so then interplanar spacing equation is there, as I told you. If I'm going to ask a question from this equation, I'll give the equation. Okay, but you need to know what are what. What is D, what is H, what is K, what is L, what is A. You need to know. And then parallel planes, they are having parallel plane means they are perpendicular distances are equal and their Miller values are related. Okay, this is clearly explained in the book. If you have any questions, let me know. And then family of planes means especially for cubic system, regardless of the order and the sign, if the Miller values are the same, then they become they belong to a same family of planes, meaning their properties, crystallographic properties are equivalent. Here is a practice question and actually the answer is given. You can try yourself and see whether you are getting the correct answer. Then defects, I'm not going to discuss because it's clearly and nicely explained in the sessions. The only thing that I want to explain is, any questions about defects? Let me know, because I don't want to be unfair to those students who are going for the biomolecular or whatever the lecture. So I'll upload today's this particular video so that you have access to it. Anyway, I want to explain this one, the thermodynamic explanation of defects, why defects are forming. Defects are forming because it is energetically favorable. In other words, defect formation is spontaneous. So this has the defect formation has a negative Gibbs free energy. Why is because of the entropy value. What do you know about entropy? What is entropy? Someone tell me, what is entropy? Sorry, what is delta S? What is entropy?
The degree of disorder.
Yes. Entropy, so that is degree of disorder or the randomness. So higher the randomness, higher the delta S value. If the randomness increases for a process, during a process, that process have a higher or a positively higher delta S value. Right? Okay. So defect formation means now the crystals are in an ordered pattern. So higher the order, lower the randomness, isn't it? So if the solid formation or the lattice formation, because it is acquiring what you call ordered pattern, that means the entropy is not positive. Okay, so but when the defects are forming, meaning that we are disrupting that ordered pattern, that means defect formation has a positively large delta S. Do you understand that? So positively large delta S value, then the whole term negative T delta S, T is temperature constant, that will be negatively large. See, minus TS, minus, okay, minus TS, the whole term is negatively large. All right. Compared to that, what about delta H? Delta H is the lattice enthalpy here. Now, when the defects are forming, the enthalpy value is endothermic because now we are disrupting the lattice. Okay, we are disturbing the lattice. Lattice formation enthalpy is positively large, and if you are disrupting that, that means it is going to be endothermic. It is going to take up energy to disrupt or disturb the lattice. So this is positive, increasing. This is for the defect formation. Okay. Not for the lattice. This is for defect formation process. So this is positive. It's going up. When higher the defects, higher the enthalpy. But the minus T delta S is going down. The resultant is delta G. So up to some point, it is going down, down, down. And then the delta H value is exceeding. And then hereafter, delta G value will be going up again. So there is an optimal condition, the lowest delta G value for defect formation. So because it's largely negative, gives free energy at that point, that amount of defects will be spontaneously formed for a solid. Okay, so I want to explain the defect formation in a thermodynamic explanation of that. So I really wanted to do that with you. So is it clear? Is it clear? Is it clear? Any questions? If no questions, I'm going to finish it or stop the our session today. All right, answers are already given for these practice questions. You can try those. And with that, we will stop. I'm sorry that I took 5 more minutes from the biomolecular students, but since I'll be uploading this presentation or today's discussion, you will have access to this. Yes, Sudha.
Ma'am, second part of the previous question, can you explain it? I asked it.
This one?
No, ma'am, you discussed previous question paper, the previous year question paper in structure question, second part.
This one?
No, ma'am, beginning of this, yeah, second part of discussion.
Number 2, what is a Bravais lattice?
Ma'am, why we consider this as a primitive cubic? Because there is 4 copper atoms in face center position. So why we consider as a primitive?
Yeah, were you there in the day school 2 lecture? Hello?
Yes, ma'am.
You were there. So I explained the same thing with the cesium chloride lattice. Remember cesium chloride lattice? You guys were telling it's a body-centered cubic lattice, but I said it's primitive. And how did I explain it's primitive? Do you remember? Go back to that video and learn again. And also in this video, I'm explaining it. This is all about lattices. Lattice points are identical. Their chemical surroundings are identical. So you can't consider these copper atoms as identical to AU points. So when you are defining a lattice, you have to consider the lattice points. So the corners are lattice points. So in corners, these lattice points are coinciding with AU atoms. So these copper atoms cannot be considered as lattice points. Lattice points are not atoms, necessarily atoms in a lattice.
Yeah. Okay.
Okay, so go back
Yeah,
and think
okay.
about it again. All right,
Yeah,
so
okay.
any other questions?
It's like, madam, that structure is similar to the body centered cubic type, but not the centered cubic structure. Is it?
Yeah, so the Bravais lattice type is here primitive cubic. These copper atoms are not considered as lattice points in this structure. Okay. So that happens because the unit cell is now defined and the corners are AU. Anyway, it's true. Let's say that you are going to draw the lattice unit cells in this structure, in this crystal solid. Let's say you are going to draw your unit cells so that you are joining copper atoms. So you are going to then consider copper as your lattice point. In that case, wherever the gold atoms are, they will not be lattice points. The logic is lattice points in a lattice are identical positions within the crystal. Okay.
It means that there is night.
Sorry, I can't hear properly. Hello?
It means, ma'am, there is AU atoms in face center is considered as a face center cube.
If there are AU atoms on these faces, then yes, of course, we have to consider because in this unit cell, the corners are AU atoms. That means your lattice points you define for this structure is coinciding with AU atoms. If these were AU atoms, of course, you have to consider them as lattice points. So then it will be FCC. But the problem here is, right now, they are not AU. They are copper atoms. Different from AU. Now is it clear?
Yeah, ma'am. Yeah. Thank you, ma'am.
Okay. Right, shall we now find out from here? Any more questions? So good luck with your CAT exam. I'll upload this presentation today because it will be beneficial to you. All right. Any other questions? No. Okay. Then have a good day.
Thank you, madam.
Thank you, madam.
Okay.
Thank you, ma'am.